So where we left off, I was saying that we rotate this thing around. What we have is we have a cone. So in the same way as I can find the integral underneath the line or the integral underneath the curve to find the area, I can also find the area inside of the cone. So I want the area of this. What I can say is I can do the integral of, so what I have is y equals x. So I could do integral of x dx. That gives me the area of this triangle. Then I can also integrate around in a circle of d theta from 0 to 360 degrees, or 2 pi radians. And we have to use 2 pi because the 2 pi is translated into like an actual distance instead of just degrees. Okay, so what we get to find the area here is we have x dx is x squared over 2, evaluated from, what we said, x, let's say x equals 0 to x equals 2. So what we have is we have, y equals. So we have x, or 2 squared is 4, divided by 2 is 2. So we have 2 minus 0, but I'm not going to write down the 0, because 0 squared is 0, obviously. So what I have left is the integration over the angle from 0 to 2 pi. So 2 d theta is just 2 theta from 0 to 2 pi, which is just 4 pi minus 0. So the area of that cone is 4 pi. Okay, and that is the actual area. You can find an area of a cone formula somewhere else, and you can check to see if this is correct. But I'm telling you that this is how you find the area of a cone. So this is like, I think that I've explained most of the basic concepts of calculus. The one area where I haven't explained is if you have 3 dimensions and I have like a cylinder that's coming down. But this is, if you understand the other stuff, should be easy. Okay, so what I'm doing is I'm integrating around this angle here, and it's at 360 degrees. So I already know that I have an integral 0 to 2 pi. Okay, I know that I have a z direction that goes from like 0 to 4. So I can integrate 0 to 4 dz. And then I also have the angle, which is d theta, and then I have like let's say this is x direction from 0 to 2. So I integrate x 0 to 2, I rotate it around the angle, and then I raise it up by 4. So what I have with calculus 3, three-dimensional calculus, is I have, so just real quick, I have x went from 0 to 2, z went from 0 to 4, pi went from 0 to, or the angle went from 0 to 2 pi, and then I have dx, dz, d theta, and I'm evaluating this in the same way that I did over here, where the answer is just going to be, dx from 0 to 2 is just 2, dz from 0 to 4 is just 4, and then d theta from 0 to 2 pi is just 2 pi. So I have 2 times 4. So the volume of this cylinder is 2 times 4 is 8, times 2, so it's 16 pi. Is the volume of the cylinder. So that's how you do three-dimensional calculus. Right, so like you might see in three-dimensional calculus, you might see acceleration as a function of x, as a function of time, and also as a function of an angle. So you'd have as an integral from x1, x2, you have an integral from t1 to t2, and then you'd have an integral from theta 1 to theta 2, where I don't have to rotate this around the whole way, right? I could have this only going a quarter of the way, where this is, if the whole thing is 2 pi, then halfway is pi over 2. So theta 1 could be, right? Theta 1 could be pi over 2. Theta 2 could be 3 pi over 2. So I need to choose my limits of integration based on the shape of the object. And this is essentially just like, in a nutshell, most of calculus. There's a few things that I didn't show you, and there's a few different strategies that you can use. But in general, this is like a good summary. If you can do all of this, then you're capable of doing all of the calculus that is from these classes. Now, there's certain things where you know, there's a few things that you kind of add that I didn't mention, but again, it's not any more difficult than what I've already showed you. Okay, it's not any more difficult than what I've already showed you. Like there's a thing where you can say, if you're doing derivatives, maybe what I didn't say is if you have x and you have dx dt, if you're doing 3-dimensional or 2-dimensional, you can't, you have to just leave this as dx dt. Right, so if I have x squared and I'm going d dy, I have dx squared dy, but this is 0. Okay, because the integral of a constant is 0, but I can't put 0. I have to put, so if I'm integrating x with respect to t, it would normally be 0, but if in 3 and 2 dimensions, you have to write it in as dx dt, you can't simplify to 0. So I'd have to write in x squared, you know,